Hey guys, how you doing? It's Coach Scott again, and we're going over our second part of atomic structure. We're going to talk about electrons and protons. So, in the late 1800s, scientists were passing electricity through glass tubes that had a small amount of a gas like oxygen or neon or whatever. So, when the power was turned on, the tube emitted light and glowed, right? So, the positive electrode was called the anode, and the negative was called the cathode. So they called these rays cathode rays because they appear to be coming from the negative end of the tube. So there was much speculation about what these cathode rays were. Were they waves or were they particles? When an object was placed in the path of the rays cast shadows of the objects placed in their path. All right, so you put a little metal thing there in the middle of the rays, so these waves cast a shadow. So it could be light, because when we have light in front of us, and we'll have a shadow, right? Or it could be a tiny stream of particles. So scientists have found that they can deflect this beam by subjecting it to an additional electric field. So why would the beam deflect toward a positive plate? Now, does this indicate the rays or light rays are particles? All right, so the right answer for that would be because the beam carried a negative charge. And these light waves, and that's what they were light waves, would not be deflected. These were particles. Okay, they would not be deflected by an electrical field. Scientists also found that they could deflect the beam by subjecting it to a magnetic field. Why would the beam deflect toward upwards in the magnetic field above? Now, does this indicate that the rays or light rays are particles? The right arm rule, when you take physics, you'll understand. In the magnetic field above, the negative charge would deflect up toward the positive end of that magnetic charge. So these are particles because light rays would not be deflected by a magnetic field. So, scientists determined that a very weak electrical field could deflect the beam a great deal. Again, a very weak electrical field. So, if these particles are really easy to deflect, they either have a small what? All right, a small mass, because smaller things are easier to move than big things, or a really large charge, a really large negative charge. It's either or. So, J.J. Thomson and his team were able to determine this charge to mass ratio to be 1.7 times 10 to the 11th coulombs of charge over kilogram of mass. Now, they had no idea what the charge was. They had no idea what the mass was. They just knew that the ratio was large, indicating either that it had a large charge or a small mass. Now, what was very interesting was that these negatively charged particles were found in all gases that they experimented on. And they all had the, check this out, same charge to mass ratio. Now, physicists proposed that these negatively charged particles be called electrons. These particles have the same charge to mass ratio as the negative particles generated by static electricity, heated materials, and illuminated materials. Now, what characteristics about the cathode ray led them to believe that they were negatively charged? Let's see. They were small? Well, we don't know. Their behavior in an electrical field? Well, yeah, we talked about that. Their behavior in a magnetic field? Yeah, we talked about that. Or B and C? Well, let's try maybe D, B and C. Which of the following indicated that the cathode rays had a large charge to mass ratio? They caused a fluorescent screen to glow. They were easily deflected. They were deflected toward a positive electrode. They were deflected toward a negative electrode. Oh man, I need some help. Well, how about that they were easily deflected? They were easily deflected, so it either had a small mass or a large charge. But there was a large charge to mass ratio. So a guy named Millikan, a guy from the United States, he had this oil drop experiment. And what he did is he squirted this oil, right, into this box. and he was able to pass high energy X-rays to the source, right? And these little oil droplets would go down into this charged plate, had a battery there, right? And by passing these high energy X-rays, he was hoping to knock off one of these newfangled electrons off the air molecule and onto the oil drop, right? And have it just hang out there. So here's some sample data he noticed. One drop had 4.8 times 10 to the minus 19th coulombs. The other one had a charge of 3.2 times 10 to the minus 19th, and that was 2 drops. Notice what we can see here. 3 drops had 6.4 times 10 to the minus 19th coulombs, and drop 4 had 9.6 times 10 to the minus 19th coulombs. Now, what he noticed is that the charges on each drop were a multiple of a number. Okay, what do you think the number? What do you think the multiple? What was the number they're all a multiple of? Let's look and see. 1.6 times 10 to the minus 19th coulombs. 1.6 times 10 to the minus 19th. If you take that, 1.6 divided by, or 3.2 divided by 1.6 is 2. That's 3. That's 4. That's 6, I believe. All right. So the charge of an electron, and that's what Millikan discovered, was what the charge value of the electron was. 1.6 times 10 to the minus 19th coulombs, and the charge to mass ratio is 1.76 times 10 to the 11th coulombs per kilogram. What is the mass of an electron? You do the math, right? 1.6, or actually 1.76, all right, coulombs divided by, well, actually I do the different way, but anyway, if you do the math, it is 9.1 times 10 to the minus 31st kilograms. Pretty small, right? So, which of these could be the charge of a drop in the Millikan oil drop experiment? Again, it needs to be a value of 1.6 times 10 to the minus 19th. C, 8 times 10 to the minus 19th coulombs. So the magnitude of the charge on an electron was determined in the Millikan oil drop experiment. Remember, J.J. Thomson determined the charge to mass ratio. Now, we found about the discovery of the electron. That's the first one we really found out about. So after the discovery of the electron, scientists believed that there must also be a positively charged particle in the atom. So to use that, to find these, right, or to look for them, they used an anode ray tube, right? So what they did was they placed holes in the cathode so the particles could move through it. They found that these particles were indeed moving from the anode to the cathode. Since they were moving toward a negative plate, they must be positive. So the anode rays we refer to as protons, which were found to be significantly heavier than electrons. One proton was determined to be 1,840 times the mass of an electron. So since the heaviest anode rays in oxygen were found to be 8 times heavier than those in hydrogen, it was assumed that oxygen had 8 protons compared to hydrogen's 1. The number of protons an atom has is different for each element on the periodic table, depending on, well, how many protons it is. The number of protons determine what the element is. Now, which of the following is true regarding protons? They were originally called cathode rays. They move faster than cathode rays. No, they have a larger mass than electrons. They move from the cathode to the anode. C, they have a larger mass than electrons. Which of the following is not true regarding protons and electrons? Both were found in all atoms. Their charges are equal in magnitude. Protons are significantly heavier than electrons. True. all elements have the same number of protons. We know that is not true. Their charges are equal in magnitude. Yeah, they were found in all atoms. Yeah. So it has to be D. All elements have the same number of protons. The mass of an electron was found to be 9.1 times 10 to the minus 31st kilograms. What's the mass of a proton? So we know that it was 1,840 times the mass of a electron. So that would be 1.67 times 10 to the minus 27th. It's a little bit bigger, so it would be A. So anyway, that's all we're going to talk about on this edition. So this would be part B about atomic origins. And so watch this whenever you can. So this is Coach Scott saying out.